going to be discussing the stability belt and in particular the stability of a nucleus. As you all might know, that an atom is made up of a nucleus is made up of protons and neutrons. Now, two protons have the Coulomb repulsive force between them. This means that two protons will repel each other and an atom might collapse, but this does not occur. An atom is stable. Now, why is that so? This is due to the presence of neutrons and the strong nuclear force. The strong nuclear force holds together, acts like a sort of glue, and it holds together the atoms, together, and prevents the atom from collapsing. So that establishes the stability of an atom. The stability of an atom is due to the presence of neutrons that act like a sort of glue, and they glue together the proton and the neutron, and everything in an atom is glued together due to strong nuclear force. That's a simple analogy to understand how the strong nuclear force works. So an atom is stable. No. So an atom is stable because of the strong nuclear force that opposes the Coulomb repulsive force between two protons on the prevents the nucleus and the atom from collapsing. Right. That means more number of neutrons should provide more strong nuclear force, and that should result in a stronger gluing force, and the atom should be more stable, right? No, that's actually not what occurs. You might have studied in Bohr's atomic model, and even if you haven't, I'm going to tell it to you right now, that an electron resides in discrete energy levels. As you go higher, the energy is increasing, and no two electrons can occupy the same quantum state. So if this electron has a plus 1 by 2 spin, this has a minus 1 by 2 spin. The same principle applies for protons and neutrons. Now, nature uh, tends to stay at lower energy. Nature favors lower energy states. Why? This is a topic for another video. I'm not going to get into too much depth here, but nature favors lower energy. So what actually is happening is protons and neutrons, they have separate energy levels. Protons and electrons, they can't intermix between each other's energy levels. What that essentially means, if I break it down into simple steps, suppose this energy level, these energy levels are for protons. These are for protons, and then I draw another bunch of energy levels right around here, like simple like this, and this is for neutrons. Now what can't happen is that these neutrons, they can't just jump over here, or the protons can't just jump over here. That does happen, but that is a conversion. That is conversion, a neutron to proton conversion, a proton to neutron conversion. The neutron itself can't occupy the energy level that the protons occupy. Right, we got that out of the way. What I meant by, if any of you are confused by what I meant by that does occur, that is actually what's happening in a beta decay. A neutron is being converted into proton. So let's suppose I'll actually discuss this later on, so bear with me right now. So what we were discussing is that if I add too many neutrons, we just discussed no two particles, no two subatomic particles can occupy the same quantum state. So if I add more neutrons, they are occupying higher energy levels, and the atom just keeps on getting unstable rather than stable. That's why the neutron to proton ratio from Z is equals to 20 remains till Z atomic number 20. Neutron to proton ratio will remain 1. The number of neutrons are not increasing because as the number of neutrons increase, they occupy higher energy levels and the atom will get unstable. Hope you understand this. One more time, just so this becomes really simplified, from atomic number 1 to atomic number 20. Hey, the neutron to proton ratio is equal to 1. Why can't we have more number of neutrons? Well, basically, as the number of neutrons increase, neutrons exist in discrete energy levels inside an atom. What that means is no two neutrons can occupy the same energy level Well, that's a Pauli exclusion principle. The neutrons cannot occupy any energy level that they want. They have discrete energy levels. Else, else discrete specific energy level that they can occupy. That means if I have energy level 1, 10, 20, a neutron can occupy energy levels 1, 10, and 20 only, not 8.5, nothing like 9, nothing like 11. Only 1, 10, and 20 are possible. And then the second concept is no two neutrons can occupy the same quantum state. That is why two neutrons occupy one energy level, other. But as the number of neutrons increase, they occupy higher energy levels. Now, as they occupy higher energy levels, we know that nature favors lower energy. The atom gets unstable. That's why from atomic number 1 to 20, neutron to proton ratio is equal to 1. Now, why can't we have more number of neutrons? Why can't this value decrease in 1? Become less than 1? Well, if the number of protons increase, we just studied the Coulomb repulsive force increases, and as the Coulomb repulsive force increases, and we don't have proportionately that number of neutrons, the strong nuclear force will become weak at one point, and the atom will simply collapse. Now, why is there a deviation? Like from z is equals to 20 to z is equals to 85, I believe. Z is equals to 85. Bismuth is the last stable element, and and why is the neutron to proton ratio equal to 1.6? For some reason, the number of neutrons in heavier elements have increased. Now, why is that? Well, dear students, you must understand that the strong nuclear force is very short range. It is 10 raised to power minus 15 meter strong nuclear force. Also, that is the range of the strong nuclear force, 10 raised to power minus 15. But as the atom gets larger and larger, what that means is the strong nuclear force will have lesser of a grip on the outer neighbors of the atom. Let me make an atom here. I'm just gonna. This is just for show purposes. I suppose as the atom gets larger and larger, these neutrons they're having a much less grip on these farther protons. These farther protons, the interaction is getting weaker and weaker, and it can't hold those protons stronger together. It can't hold the atom. It can't glue the atom um, um, uh, in a way that it did before because it's very short ranged, which means that you gotta increase the number of neutrons. I gotta add some neutrons here as well so that they can glue these protons that are getting farther and farther and farther, or as the atomic size increases, basically. This has to do with the atomic size becoming greater as the number of protons increase, and the strong nuclear force is a very short range force. You gotta remember that. That is why the number of neutrons are increasing, so that the strong nuclear force can still exist and heavy atoms can remain stable. sometimes, sometimes, while you see in heavier elements, the number of neutrons are increasing. This means that neutrons are occupying higher energy levels. Well, most elements won't want that, right? That's when beta decay and alpha decay comes in, which is a topic for future energy levels. Future, oh my god, future videos. Until then.